Good morning and welcome to Statics, EGE 2013 here at Lawrence Tech. For those of you who don't know me, I'm Jim Kearns, professor here. Mostly I do robotics, but I teach statics as well. So I'm preparing this whole series of videos here to kind of go through the course and give you examples of things. So if you're stuck on a particular problem, particular concept, I'll be giving you examples that you can follow through. I'll be explaining them in, I hope, excruciating detail. The other purpose of these videos, of course, is if you're having trouble sleeping, they'll be perfect, right? But for this first video, we're going to kind of give you some background information. We're going to talk about the definition of statics. What do we mean when we talk about statics? And some background stuff like units. We'll cover the units that are found in your book. We'll cover some other units that I think you need to be aware of. We'll talk about significant digits, and that will be this video. And then the rest of the videos, like I mentioned, will be mostly examples, mostly on the computer screen, so you don't have to look at me. You know, I mean, nothing exciting here, right? But we'll work through those. So let's get started. What is statics? I'm going to insert this in the beginning because I completely skipped over. So you'll notice there's no continuity in what's on the board, and it's bad editing, and that's life, right? Statics is the study of the forces on objects in equilibrium. Okay? If we take Newton's law, force equals mass times acceleration, statics deals with the cases where the acceleration is equal to zero. Okay? We've got some object here. I've got a marker. As I hold it, obviously there's gravity, a force of gravity pushing it down, force from my hand holding it up. It's in equilibrium, it's not moving. Or it could be moving with a constant velocity. There's no, acceleration is zero, except for when I change directions at the end. Okay, so it's in equilibrium, and I can sum up the forces, and really we should write this as the sum of the forces equals ma, where a equals 0. Okay. If I hold it at an angle here, let's see if I can do this without it falling. Okay. Now I'm applying a force upward to hold the force of gravity, but there's also friction going on here, and all those forces balance out, and this marker is not accelerating, it's not moving. So that's what statics is. It's a study of objects in equilibrium. We'll look at balancing and determining all the external forces. What are the forces on this device as I hold it? I can hold it this way. As I squeeze on it, I put a weight on it in the middle. We can calculate what the forces are, what unknown forces are. We can calculate the forces inside this marker. As I squeeze, it's under compression. If I try to do this, it's in bending, so I've got compression on the top, tension on the bottom. We'll figure out all those forces internally. And then this is the foundation when you move beyond statics to dynamics, where acceleration is not equal to 0. Okay, which we can talk about the motion of things. But a lot of what we'll do here in statics is the fundamentals that you'll be using. And as we go through this course, we're going to start with simple examples, simple cases, and we'll just keep building and building layers of complexity. Okay? Back to our regularly scheduled program, already in progress. As you can see, I've already written a bunch of stuff on the board here with various sets of units, and we'll walk through them. The ones we're going to use in class here are primarily the SI units here and the pound, slug, foot system, but we'll go through these. SI units, if you have any control over what you're doing, use SI units, please, okay? Life would be much better. Okay, but the SI units, the unit for length is the meter, time is second, mass is kilograms as the base unit. That gets a little bit confusing sometimes because it's kilograms and not grams, so you don't forget that, please, because when you're applying Newton's law, you're going to need to use kilograms and not grams. Okay, but base unit of mass is kilogram. The unit of force is Newton, named after Sir Isaac Newton. When you want to apply Newton's law, newtons equals the mass in kilograms times acceleration in meters per second squared. If you want to calculate the force due to gravity, you need the acceleration of gravity. On the surface of the Earth, the standard gravity acceleration is about 9.81 meters per second squared. So if you want to calculate the force due to a weight, the weight due to a mass, that force is newtons. And we'll be doing this a lot as you calculate forces in structures and beams. Newtons equals acceleration of gravity, 9.81 meters per second squared, times kilograms. The other unit that we will use in the course of EGE 2013 statics is this one here, where the unit of length is the foot, unit of time is the second, the unit of mass is the slug, the unit of force is the pound, and to apply Newton's law, we just say that F equals ma, pounds equals slugs times acceleration in feet per second. If we need the force due to gravity, our force due to gravity in pounds is equal to the mass in slugs times acceleration of gravity of 32.2 feet per second squared. Now those are the ones we're going to use in the class. I expect you to know those and have these numbers like 32.2 and 9.81 memorized, because you will need them. But I want to talk about some other units because you're going to be exposed to them. I've run into people that they'll say, well, they learned this system here in school, and you start talking about pounds force, and they just pounds mass, and they just say, well, no, pounds is force and slugs are mass, and they don't understand that there are other commonly used, widely accepted systems out there, and you end up looking like an idiot, okay? I don't want my students to do that. But let's go back to metric for a system, lest you think that metric is simple and it's convenient and it's always right and it's always consistent. No, I wish. Okay, this is an older system, CGS, where the unit of length is not the meter, it's the centimeter, and time is the second. And instead of kilograms, they use grams, okay? The unit of force in this case is the dyne, and a dyne equals Newton's law. To apply Newton's law, F equals ma. Dynes equals mass grams times acceleration in centimeters per second. Okay, so you got to keep this straight. Is it centimeters? Is it meters? Is it grams? Is it kilograms? And the force of gravity in dynes is 981 centimeters per second squared times mass in grams. Okay, there is another metric system out there that unfortunately some of you will run into. If you can avoid it, please do. If you can't, I've had students that this is what they use where they work and you're just stuck with it. It's a bad thing in my opinion. Excuse me for editorializing. But in this case, the length again is the meter, time is seconds, mass is kilograms, like it has been all along, and then they introduce a kilogram force. This is not SI. This is just a way to pervert and confuse people, because what people will frequently do is they'll just write kilograms, and you're supposed to figure out from context, is it kilograms force, kilograms mass? That doesn't work. Answers are typically off by a factor of 9.81. It's just a bad thing, okay? So if you're going to use these units, then you want to put a subscript M and F just to be clear in your writing, or write it out kilograms force, F-O-R-C-E, okay? If you don't, I'm going to come back and haunt you, okay? I'm an old man. I'm going to die soon. I'm going to do that, okay? So don't be that guy. The force due to gravity is simple. Kilograms force is just simply the kilograms mass, and that's convenient, and that's why people use it, because they can just say, well, this car weighs 2,000 kilograms or whatever it weighs. But when you apply Newton's law to do any dynamics, you have now kilograms force is equal to kilograms mass over little g times A in meters per second. And little g is 9.81 kilograms mass per kilograms force meters per second squared. So you can't get rid of that 9.81. It's there. It's there. You just moved it, okay? And you moved it into a place that's not standard. And it's just, you know, don't do that, okay? Like I said, I will come back and haunt you. We talked about this unit. Another common pound English unit system, and this is the one that I used as an undergraduate way back in the olden days, you know. Back then we didn't have YouTube and video cameras and things like that, and you know, we had television, but we didn't have electricity, so we had to watch TV by candlelight, right? Okay, but this is what I commonly used as an undergraduate. Length is foot, time is seconds, mass was pounds mass, LBM, force was pounds force. Applying Newton's law, pounds force equals pounds mass over g, and times acceleration in feet per second squared. Here g, little g, is 32.2 pounds mass per pounds force, feet per second squared. Believe me, I have that burned into my brain like you wouldn't believe. All those years. That'll probably be the last thing I'll forget before I die. You know, I may get senile, but I'll remember 32.2 pounds mass per pounds force, feet per second squared. Okay, enough about me. Another one you'll run into, just for the guy that thinks that you know, this is the only one, you know, pounds are force and slugs are mass. Here's one where mass is pounds mass and force is the poundel. Okay, we've completely flipped the pound. We moved it from here to there. Okay, foot and second are the same. And Newton's law here, the force in poundels is the mass in pounds times acceleration in feet per second squared. And if you want the force of gravity, the force in poundels is the mass pounds times 32.2, assuming a standard gravity here on the surface of the Earth. Okay, so those are the basic units. I'm going to take just a moment to talk about units of pressure because there's just so many of them. And oh, I should mention what's going to be on a test, right? These two you'll need to know. The CGS, MKS. MKS system, meters, seconds, kilograms, newtons, okay? You'll need to know that. Foot, second, slug, pound, you'll need to know that, okay? These others won't be on a test, I don't think, and you know, of course, you may not be taking my class, you may be taking it from somebody else, but those are for information, okay? Just so you don't look like an idiot when you get out there and try to tell somebody that these units don't exist. Well, they do, okay? So we're going to talk about pressure just because there's such a variety, and I'm not going to go through all of them, but just, again, awareness. Okay, so let's talk about units. Now, I've, again, written these out ahead of time and done some drawing so that, you know, if for some reason you're compelled to take notes, you know, obviously you can pause the tape and write things down so that you have that for your notes for class. But otherwise, I'm trying to save a little bit of time. So let's talk about pressure. And I don't mean, you know, there's an exam coming up and, oh my gosh, I'm under pressure. No, okay. The first thing we need to be clear about is gauge pressure versus absolute pressure. You can use the same units in either case, but what you mean is different, and how you measure it is different. Gauge pressure is what you would typically measure with a standard pressure gauge on some kind of container. You know, you've got a oxygen tank for your welding system, and there's a gauge sitting on top. That's gauge pressure, and it's called gauge pressure, well, because it is. But gauge pressure is the difference between the pressure in your container and atmosphere. And I've drawn a couple pictures here. And the other form of pressure is absolute. But for gauge pressure, if I have a container of water here, and I screw a pressure gauge in 1 meter down from the surface, okay? And I measure the pressure. Well, the pressure due to 1 meter of water is 9.8 kilopascals, okay? So my meter in gauge pressure is going to read 9.8 kilopascals here because it's referenced to the air. So the fact that there's air pressure on top of the water, the same air pressure is inside our gauge, and that all cancels out. An absolute pressure is the pressure relative to a vacuum, not to the surrounding air. It's the pressure all the way back to a vacuum. So if we look at this case, if I had an absolute gauge here, I have 1 meter of water that gives me 9.8 kilopascals. I have atmospheric pressure on top of my container, that's 101 kilopascals. So I'm going to say, I'm going to be reading something on the order of 111 kilopascals absolute compared to the 9.8 kilopascals gauge, okay? That's a big difference, right? 9.8 versus 111. So that's why you need to know what are you referencing to, okay? Now here in an oxygen bottle where I have, and I'm going to switch units on you here, a couple thousand pounds per square inch, that extra 14 pounds per square inch of atmospheric pressure, no big deal, right? But in most engineering applications, it does make a difference, and you need to know which one you got, okay? So that's gauge versus absolute. If you're not clear on that, look at the pictures, rewind, whatever. And in all these videos, as I do the examples, pause the video, work the example yourself, write things down, and get it really stuck in your head. Okay, so let's talk about common units. The SI units are probably the key here. The unit of pressure is the Pascal, named after the mathematician. A Pascal is defined as 1 Newton per meter squared. Okay, so if I apply a force of 1 Newton spread out everywhere on a 1 square meter, I get 1 Pascal. Standard atmosphere is 1013.25 hectopascals, and I'm pointing that out because pascals is one of those goofy units where people actually do use hectopascals. It's the only one I know of that they use the hecta prefix. Hecta is 100, so a hectopascal is 100 pascals. Don't get thrown for a loop when you run into those, okay? It's just 100 and you'll just remember that. Another very common measure of pressure is the bar. A bar is 100,000 pascals, and standard atmosphere is 1013.25 millibars, which happens to be the hectopascal, and that's why they use the hectopascal, because weather guys for years and years and years used millibars, and they just changed the name of the unit, okay? so their numbers are the same. They still use 1013. It's still 1013 because it's hectopascals and it has the same magnitude. A standard atmosphere is 101.325. See that number again? Kilopascals, okay? And a standard atmosphere is 1 atmosphere. So you'll see a lot of things expressed in atmospheres. I hope I'm getting out of the way so you can read. I will warn you, there's also a technical atmosphere that you're likely to run into. This is another bad one, okay? It's just bad because atmospheres and technical atmospheres, why? Okay, technical atmosphere, AT, it's 1 kilogram force. You remember the kilogram force from a minute ago? Bad, okay? Per centimeter squared, and a standard atmosphere is 9.67 atmospheres, okay? So it's almost the same as an atmosphere, but not quite, and it's just different enough to cause problems. Non-metric units, very common, millimeters of mercury. Oh, that's still metric, I'm sorry. Well, you can argue whether it's metric or not. It's metric, it's millimeters. It's not SI. Okay, a millimeter of mercury is 133.3 pascals, or you can look at it as the height of a column of mercury that is the pressure to support a column of mercury 1 millimeter tall. What does that mean? Height of mercury, why did that come about? If we look at this as our old-fashioned mercury barometer, where you have a tube sealed at the top You initially fill it with mercury, you stick it in a pool of mercury, and then you stand it up, and then you end up with a vacuum up here because the atmospheric pressure pressing down here can only exert so much force and force the mercury up this tube, and then up here you end up with a vacuum, or very close to a vacuum. And then you can measure the height of that column of mercury, and at standard atmosphere it's about 760 millimeters of mercury. But because this was the common technology for measuring pressure, the units came out to be something easy to measure using that technology. We just put a meter stick there and you can measure your pressure. Okay? So that was millimeters of mercury. The non-metric version of that is inches of mercury. If you listen to a weather report here in the U.S., they'll talk about the pressure in inches of mercury, 30 some odd, 29 something, whatever it comes out to be. A standard atmosphere is 29.92 inches of mercury. It goes up and down with the weather. Another measure you may run into is inches of water. You can run into millimeters of water. It's the same concept. It's the amount of pressure that will support a column 1 inch high of water. And a standard atmosphere is 407 inches of water. And very, very common is pounds per square inch, or PSI. By definition, that's 1 pound force per square inch, right? Hence the name, pounds per square inch. And a standard atmosphere is 14.696. We won't be using those in the statics class, but I want you to be aware of them, okay? Next up, let's talk about significant digits, okay, as our last bit of introductory stuff here. What do we mean by significant digits? When I write a number, you notice here I wrote 101325. I've got 6 digits there, right? Okay, so there are 6 significant digits. I'm writing it with some degree of precision, okay? Does this make a difference? Is it important? Oh, it's huge. It may not seem to be a big deal, but as an engineer, you really want to be careful. Okay, here I have the textbook. Should I do the Vanna White thing or whatever? Here's our textbook, right? How much does this weigh? I want to know how much this weighs, and I want to know how much moisture is absorbed. It's kind of damp today. This paper has absorbed some water. I want to know how much moisture is in that book, right? So I'm going to dry it out and see. So first of all, I need to know what's my starting weight. If I heft it here, I come out to be, it's about 1 kilogram, okay? Just by feel, okay? So I've got this book. It weighs 1 kilogram. I can convert that into pounds. And when I do, I come up with, this book weighs 2.2046262 pounds. Mass. Okay? That's the mass of my book. Now if I take this book and I throw it in the oven in the lab next door, and I leave it there for 24 hours at, say, 220 degrees, it'll boil out all of the moisture, right? So I can take this book out and walk it into one of the labs that has a very sensitive scale and put it on a scale, and I can weigh it, right? And the difference between this weight and the weight that I get is going to be the weight of the moisture, right, that I drove out. Does that make sense? Okay? Am I going to get a decent answer, right? I can put it on a very sensitive scale, and I'm going to get, let's say I'm going to get 2.45678 pounds when I put it on a scale. What happened, right? When I do my subtraction, according to this, I gained weight, right? Well, what's happened should be obvious. I didn't put this on a scale. I just sit here and hefted it and said it weighs about say it weighs 1 kilogram. Well, how accurate is that, right? 2.62 pounds when I did actually weigh it, by the way. Oh, so that should have been make that a 6. But what I did was I took this, I don't know, feels like 1 kilogram weight, and I did a conversion to pounds, and I gave you 1, 2, 3, 4, 5, 6, 7, 8, 9 significant digits, if you didn't know that I just done this hefted and this conversion, I just gave you this number right here, you might assume that I have a very precise measure of the mass of this book, right? I mean, I know to the 9th significant digit how much this weighs. That's a very precise measurement, except that it wasn't. You know, I just hefted it. I'm lying to you. When I write this out to 9 significant digits, I'm lying. Okay, I'm giving you information that does not exist. I'm misleading you. I'm giving you too many significant digits. At best, we could say that. Okay? And even that, really. I mean, 1 significant digit, that's about all I get from bouncing this book in my hand. It's about 2 pounds. Now when I say, okay, I'm going to go dry this book, and it weighs about 2 pounds now, and I'm going to drive, you know, 1/100 of a pound of moisture out of there and compare the difference, you're going to look at it and say, no, it's not going to work, okay? So the significant digits, in general, you don't put more digits than those that are real. If you put all those digits there, these digits were not real, they didn't mean anything. At best, they're nonsense. At worst, they're misleading, and they're going to cause somebody to do stupid things, okay? So that's why significant digits are important. Typically for this class, we will work to 2.20 would be, say, 3 significant digits. For most engineering applications, that's pretty good. 3 significant digits gets you within 1%. So be careful. Okay, 3 or 4 digits for about anything in this class is all you're going to use. But in the real world, you know, don't just say, well, I'm always going to use 3 digits or 2 digits or so many digits. There are times where you may want to weigh this book and get, you know, 6 or 8 significant digits because you want to do that experiment and dry it, okay? If those digits are real, use them. If not, they're not, okay?